So welcome to the 9th lecture. Today we'll be discussing perfect graphs, which is like a very nice, I found it very nice and very cute topic, but somehow like detached from the rest in the sense. I mean, maybe Michał's lectures in the week on K-boundedness will somehow connected to the rest, but somehow like the things we'll see today will be like about colorings, but to my thesis they will be like much different in favor than the previous one, than what we did the previous time for planar graphs. Yeah, so let's recap what we did. We're discussing really like on a high perspective. We're discussing some like difficult graph questions or difficult graph invariants, I would say. Yeah, so these were really difficult graph invariants. So we discussed mostly the chromatic number. So how many colors you need to use for vertices to color the graph so that no two adjacent vertices have the same color. This is what we defined last time. But also there was in connection with that were size of maximum clique in the graph, like here, the 4-vertex clique, and maximum size of the independent set here of size 3. Yeah, and we had this. So these were like the main invariants we somehow discussed last week or partially discussed. And we had this trivial observations at some moment that, okay, I mean, the maximum clique is nowhere larger than the chromatic number because in a clique you need to color every vertex with a different color. But also there's a second observation here that, I mean, if you color a graph, then every color class, like properly colored graph, then every color class is an independent set. So you need at least like the number of vertices time divided by the size of maximum size of the independent set colors, because one color can be of size maximum, like alpha is the maximum size for the independent set. Okay, and I will be using here the sort of like standard notation where chi is the chromatic number, omega is the clique size, maximum clique size, and alpha is the maximum independent set. And sometimes in some proofs, the graph will be obvious, so I will drop this O of G. I mean, the graph in question will be obvious, so I will drop the argument here, but that will appear in some proofs later. Okay, and now we have got these inequalities, but the inequalities in general are very, very, very weak in the sense that they're sometimes useful, but there can be like different, largely in particular, there is something we won't discuss today. There's a construction of Erdős, which is like a simple randomized construction that shows you that there are grids that don't have cliques of size 3, so they don't have triangles, but they have large chi, they have large chromatic number because they have small omega. So because of this inequality, because like the alpha is much smaller than the number of vertices in these graphs, so actually you need a lot of colors. Okay, and this is like the intuition is just that if you just take n vertices and every edge flip at random with good probability, then like something slightly larger than constant, then you will have got very little triangles, so you can delete them by some small changes. But on the other hand, you won't have large independent sets because there are still too many edges for that. So this is like the intuition about this construction. So in a sense, like these parameters in general graphs are like weakly related with each other. And the fact that they're hard to understand and how to describe is also represented on the algorithmic side. I mean, from the probably if you attended advanced algorithms course or even something basic, you know that like checking if a graph is free colorable. This is an NP-hard problem, one of the like very first NP-hard problems. Actually, at this year at the algorithmic course, this was like the root of the reductions at the beginning, and then we connected it to FreeSat. But also like the other things are not only NP-hard like alpha and omega, but are even very hard to approximate. I mean, distinguishing like graphs with like independences of size n to the 0.1 and n to the 0.9, this is an NP-hard problem, which is actually hard. I don't want to exactly discuss here the assumption behind this, but these are like believed to be hard. Probably hard. Okay, so what we did last week, we looked at planar graphs, and we said that in planar graphs much more can be said, and we discussed some things in planar graphs. And planar graphs are like a very nice graph class here in the sense that things become more structured. You can say a lot, but they're still not trivial. I mean, in some graph classes, many of these questions become trivial or very easy. In planar graphs, they're like, you can say more than you could in previous slide in general graphs, but there are still difficult things there. Yeah, so in the graph classes, we discussed the 4-color theorem last time, that chi is bounded by 4 in planar graphs, and it was a difficult problem. I mean, 5 colors was easy and 4 colors was difficult. But on the other hand, it's still non-trivial, like distinguishing. So now for planar graph, you've got like chromatic number 1, 2, 3, or 4 are like 0 and 2, 3, okay? 4 or 4, yeah. But like the cases 0 and 1 are like empty graph and edgeless graphs. So these are like these stupid cases. Chi2 is bipartite graph, so they're easy to recognize even general graphs. But then you have got chi equal 3 or chi equal 4, and distinguishing planar graphs with chi equal 3 or chi equal 4, this is an NP-hard problem. So we don't have any good, we don't hope to have any good descriptions which guys are free color, which guys are not. But actually, I mean, there are some interesting results here. For example, there's something like Theorem of Gretschel that says that if you don't have triangles, it's free color. So like planar graphs without triangles, you know what their chromatic, you can recognize the chromatic number what it is because they are bipartite and the chromatic number is minus 2, or they're not bipartite, and then you know that the chromatic number is free. You can free color triangle free planar graph. So this is a theorem of Gretschel. This is a non-trivial theorem. We don't prove it here. But you also can say that, okay, the clique number is bounded by 4 simply because K5 is not a planar graph. And because the chromatic number is at least 4, you know that there's an independent set of size that is 1/4 of the graph. And yeah, just because you can color it 4 colors, yeah. So you have got some at least like a constant. I mean, omega is easy, and like you have got some constant approximation of alpha. And actually, there is like the classic Baker's technique, which I don't want to go into this because this is not really an algorithm course, but there's an approximation scheme for alpha, so you can get as good approximation as you want. It's NP hard to find alpha, but like you can approximate this as you wish, with as good approximation as you wish. Okay, so things become like in planar graphs, things become more structured. You can say more, things become easier, but they're not very trivial. I mean, there are still difficult things, and there are still a lot of things to say about coloring planar graphs. That's why we spent the previous lecture entirely, and you can spend a lot of time on like different variants of colorings of different restricted planar graphs out there. Okay, so this was like a recap of like high-level overview of what we did last time. And just to connect, and now we are going to like take a different restriction. I mean, we are going to do a very like perpendicular restriction to taking planar graphs. Namely, we'll be looking at perfect graphs. So I here draw an example of a perfect graph. We'll discuss some tutorials why this type of graphs are perfect. This is something called interval graph. So in this picture, let me change color. Every interval is a vertex of your graph. So you have got a vertex in every interval, and you have an edge if they overlap. So if there's an overlap, you have an edge between the vertices. Okay. So this is like really looks like that. I mean, okay, there's a lot of edges. There's actually quite a very dense graph. So you have got something called interval model of a graph. So this is called interval graph. Yeah, and interval graphs are subsets of perfect graphs. We'll define perfect graphs in a moment. But I mean, I just wanted to show you as an example here, as a picture here, like one of the things that will be a perfect graph. We'll recognize the moment it's a perfect graph. And yeah, so just to understand this picture, like every interval is a vertex and overlapping guys are adjacent. Overlapping vertices are adjacent, okay? But with perfect graphs, I mean, this is not the definition of perfect graphs. This is the definition of interval graph. With perfect graph, we are just, so previously we look at the planar graphs, and just maybe by accident, or maybe we're lucky to find that this is actually the graph class when a lot of things can be said about colorings, but things are non-trivial there still. And with perfect graphs, we are taking another angle. We're looking really at the at this inequality that omega of G is smaller than chi of G, and we ask ourselves the question: what happens if we where this is equal? Where we have got the where you have got equality here, for which graphs there's inequality here. But you need to be careful with what you ask for or what you wish for, okay? Because say you have got a graph, some graph G, and you just look at this chi of G and just take a union with a clique of size chi of G. So this is clique of size chi of G, okay? And if you take a union of this clique, then the chromatic number equals the clique number because you just artificially added a clique of the size equal to chromatic number, and you have got equality, but this looks so in a sense, looking at the graph when there's equality here, just as this direction on its own, looks like a bad idea, because you have got these things like arbitrary graph plus a clique of size equal to the chromatic number. And this seems like you can't say anything about the structure of G. I mean, this can be an arbitrary graph here in this picture, just we have got like the equality here. So what we want here is that we need to add some regularization assumption or some like structure assumption, and we want to look at the graph classes that are closed under vertex deletion. So we want to add, so we want to have got a graph class where chi of G equals omega of G. So we are asking ourselves the question, hey, what happens if you assume that omega equals chi, but you also like close under vertex deletion? Yeah, this is in some sort like the simplest or the weakest closure property. Yeah? I mean, closing under taking subgraphs, like deleting vertices and edges, this is more. Closing under minors, it's even more. But like closing under vertex deletion is like the least you can possibly think about regular. So like if your graph is in your graph class, then any induced subgraph of this one is in your graph class. So yeah, so we are essentially asking here, like the perfect graphs is like the graph class, the maximal graph class that's closed under vertex deletion and has got this property that chi equals omega. Yeah, so in other words, the formal definition is like for every induced subgraph, chi equals omega. Yeah, this is the perfect graph. So this is the definition of a perfect graph, that for every induced subgraph, so for any set of vertices, if you look at the graph induced by these vertices, chi there equals omega. And this is exactly the same what I said on the previous slide, that this is like, hey, I want all the graphs where chi equals omega, but I want my graph class to be closed under vertex deletion. And what's like the maximal set of graphs that satisfy this one. Those are exactly these graphs. Yeah, I mean, yeah. So this is like the, I mean, so we are asking ourselves the question, okay, how the graphs where this chi equal chi larger than omega inequality, how is with equality? What's this, how does graph calc look like? And now this example of like decision and clique no longer works, so maybe there's some structure there. And actually it's super surprising that actually there's so very, very much structure, and this graph class is very strange. In a sense, it captures a lot of graphs, a lot of different graph classes, and have got quite a long structure. And what we will do on tutorials, we'll check in a week that actually interval graphs like that ones are perfect graphs that you can actually, so to color, so obviously interval graphs are closed under vertex deletion. So like deleting a vertex keeps you interval, you just delete the segment from the model. So what you really want to check with interval graph is that you can color it with omega of G vertices, the colors. Yeah, this is like the question, because if any interval graphs can be colored with omega of G colors, like omega of G colors, then I mean interval graphs are perfect graphs, because an induced subgraph of interval graphs is still interval, so it can be colored with omega of the subgraph colors. Okay, so yeah. So now, okay, so now let's look at some like super like abstract thing. So we have got a property. So we have got a, so think of like an abstract way of like all the graphs. So all the graphs, like this is a cone of all the graphs, there are smaller graphs lower. Okay, and you have got the perfect graphs that are like here. These are the perfect graphs. And they're closed under vertex deletion. So if you delete a vertex, you're still perfect graph. Okay. So what we can look here, I mean, actually, I should draw it differently. I should actually, drawing perfect graphs should be actually drawn like that. Maybe actually they should expand. Sorry, I will just draw it like that. Okay, these are perfect graphs. So whenever you go to do the vertex deletion, you're still perfect graphs. Okay. And now the question is like, what are like the minimal guys that are not perfect? I mean, what are the guys like that are like in a sense perfect critical? Which are the, what are graphs H that are not perfect, but whatever you delete, you are perfect. Yeah, so this is like the obvious, the first philosophical question you're asking on a high level. Yeah, you have got your graph class, and you know that it's closed under taking vertex deletion. So there's some order, some partial order in which are closed. And now you're asking, okay, what are the minimal, disorder minimal, vertex deletion minimal guys that are not in your graph class? Yeah, because you can say that the perfect graphs, like let's call this family F. This is the family F. So you can think of like perfect graphs are exactly the F3 graphs. Yeah, the graphs that don't have anybody from F as an induced subgraph. Yeah, if you look at this like F guys being the minimal guys here, like, okay, if I have got another gray guy somewhere here and I want to check, is this guy perfect? I want just to check if any of these blue guys is induced subgraph. If yes, you're not perfect because you have induced subgraph that's not perfect. That's not perfect. If you don't have any of these guys as induced subgraph, you're actually perfect graph. Okay, because I mean, these are the all minimal guys. Okay, so this is yeah, so this is like a natural way of thinking. We did it with minors. Yeah, we did it with minors. What are like the minor minimal, and now we are looking at the subgraph minimal. Now we use subgraphs. It's obvious that I mean there can be infinitely many of them. Actually, for perfect graphs, there are infinitely many of them. And one of the natural examples that comes into mind are even cycles. So if you look at K5, this has got omega equal 2, but chi equals 3. Okay, and if you look at, I mean, 7, now if I can draw 7, yeah. If you look at 7 versus cycle, again, you get omega equal 2 and chi equal 3. So these guys are perfect. They are not perfect, but if you delete any vertex, you get a path, and the path is perfect because it has got both omega and chi equal to 2. Okay, so these are definitely minimal. Okay, and one of the deeper theorem that I won't prove it here because it's a very long question, and this was actually a conjecture for a long time, a conjecture of Berg for a long time, and then it was proved in the early 2000s. This was essentially a big part, I think it was a big part of Maria Szczudnowski's PhD thesis, but also I'm not exactly sure here, but there was like, I don't want to like miss any, don't want to try to say here all the authors because I haven't prepared them, and I don't want to miss anybody, but this is something called the strong perfect graph theorem. Which is a theorem saying that the minimal guys for perfect graphs, the minimal guys that are not perfect, the vertexation minimal, are odd cycles and the complements of them. We'll check on the tutorials that the complements are not perfect, but any new subgraph after addition of vertex, it's already perfect. But I mean, these are the guys that are not perfect, and people after the definition of perfect graphs a few decades ago quickly realized that these are the minimal guys that are not perfect. And there was a long time a conjecture of Berg that actually, Berg conjecture that actually these guys are the only minimal guys, and it was proven long ago in early 2000s, like that this is actually the case, and this is called something which is called the strong perfect graph theorem. Okay, there's also a weak one. We'll discuss it tomorrow later, but okay. So one observation comes to place. So these are the minimal guys. Let's assume that we know that this family is closed under taking complements. Okay, we have got a odd cycle and the complement of odd cycle. Okay, which means that if you know, it follows that if G is perfect, then the complement is perfect. That the class of perfect graphs is closed under complement. And this is something, I mean, that at least for me comes out of the blue if you just look at the definition. If you look at the induced subgraphs, this is obvious, but if you look at the definitions, why on earth this should be happen that like the complement, I mean, coloring complement is something very different than coloring the original graph. Yeah, like coloring complement is essentially covering the graph with clicks. Right? Coloring the graph is covering the graph with independences, and coloring the complement is coloring the graph with clicks. And suddenly these guys are somehow related with each other. Yeah? And in the complement, omega becomes alpha. So as we will see from the proofs, it's sort of like the intuition is that in graph class, in perfect graphs, it's that, hey, it's that in some sense, this alpha and omega are somehow like very symmetric, like clicks and independences. They're sort of like perpendicular objects in the graph. And I mean, maybe that will be visible in the proof that actually this actually makes sense. So this statement is actually called the weak perfect graph theorem. And this is a theorem of Lovász, much older, much older, and we'll actually prove this one. So we'll actually don't prove the strong perfect graph theorem because it's really a theorem about like decomposition, how you decompose. I mean, it's really like deep structural result about the structure of perfect graphs. We'll actually prove this statement, and this is a theorem of Lovász from a few decades ago, and yeah, and this is actually quite a neat proof that maybe give you some insight how does perfect graphs work. Okay, good. So yeah, so we have got this property. So what properties we have with perfect graphs? We assumed this one and closed under reduced subgraphs, but also like the weak perfect graphs is theorem says it's closed under complements, and this is like a deep and surprising statement of perfect graphs. The other thing that we won't discuss today, because it's actually also quite difficult, is to say that actually alpha and chromatic number, alpha and omega, I mean, all these are polynomial time computable in perfect graphs, which is again surprising for me, but yeah, you can color optimally perfect graph then, and there's actually some deeper reason behind it. We won't touch these reasons today. Okay, good. So before we go there, I want to set some ground for Michał next week. Before we go into the proofs today, I want to set some ground for Michał for next week. Namely, I want to set up some notion that we started using today and want to be explicit about it. We're discussing graph classes that are closed under vertex division. Okay, so we're discussing graph classes that are closed under vertex division. They're often called hereditary in the literature. So this is like being closed under vertex division. And this is essentially some sort of like a weakest assumption of some that we are looking at somewhat nice graph classes and some arbitrary like graph clicks of prime size and something, but just like something reasonable. Okay. And now we did this like dual thing, like you looked at the minimal, like with the minors, we looked at the minor minimal guys that are not in your graph class, and the key of the Robinson-Similarity theorem was that the set is always finite. Here we don't have this property, but we can still look at the minimal guys that are not in graph class, and this is usually called H3 graphs. So if H is the family of the guys that are not in your graph class, then your graphs are H3. Okay, so we used H minor 3 previously. Now we are using H3 for induced subgraphs. That's like the things how it's used in literature. And usually, if H has got one graph, it's usually abbreviated to just H3. Okay, so for example, Michał next week will be using like PT3 graphs, like graphs that don't have induced path of some length. Here, for example, we are looking at like 6 vertex path. So T is a T vertex path, and this is so this P6, this graph is P6-3, there's no induced subgraph. I mean, there's a P6 here, but it's not induced. There's it's not an induced subgraph by this vertex, but here in this graph, this is really induced. Or like there are just 6 vertex paths and no extra edges in this graph. Okay, so this is there. And if you write in this statement, like perfect graphs are exactly like the guys that don't have odd holes and complements of odd holes or odd cycles. They're sometimes called holes in the literature, like induced cycles are called holes in the graph. Okay, and yeah, so today we are discussing perfect graphs, and the next lecture Michał will be discussing in a sense for which which other graph classes have got similar properties to perfect graphs. I mean, in a sense, perfect graphs are like the maximal family where chi equals omega, and Michał's main question will be, okay, let's relax it to like chi being like twice omega, or being omega square, or being something like that, being some function of omega, and that will be like the Michał's tasks. Michał's thing next week. Okay. So this is the high-level picture, or like the story we're doing here. And now we are actually going to prove the weak perfect graph theorem in the next few slides. So let's recall the definition. So the definition of the graph class is that, every induced subgraph has got omega equals chi. And we want to have one lemma. It's like, again, an observation of Lovász. That was like, it's like actually a pivotal question. Like, I want to have the operation that I have a graph. I pick some vertex there, V. It has got, say, 2 neighbors. Okay. And what I do, I add a clone of this vertex. So I add a new vertex called V prime, make it adjacent to V, and make it adjacent to the neighbors of V. So I'm taking, it's sometimes called making a true tree. So I'm taking a vertex, I'm making a clone with the same neighborhood, and also adjacent with the original vertex. Okay. So this is like the operation of cloning, and the observation of Lovász is that if you take a perfect graph and clone a vertex, you're still perfect. And this is non-trivial, yeah? So let's prove it. Yeah, so that's just the statement correct. I'm just saying that if a graph is perfect, then cloning a vertex after cloning one vertex is perfect. So what do we really need to check? So let's look at the definition. Okay, let's look at let's go back to this picture that was here before, and let's look at the definition. I have got this graph being perfect, and I want to prove that after cloning this guy being perfect, it's being perfect. Okay, so I cloned this guy. It's adjacent to the same guy as this guy. Okay, so what do I want to check? I need to check that this new graph with the prime called G prime, that with this in the new graph, every induced subgraph has got omega equals chi. Okay, so what induced subgraphs do we have? So we have got induced subgraphs hidden completely in G, but these guys have got omega equals to chi just because G was perfect. Okay, that's because G was perfect. So we're only really interested in induced subgraphs that contain V prime. Okay, and if I have V prime and not V, this is also like isomorphic to induced subgraph. If I have got like something looking like this is also isomorphic to induced subgraph of G, because I could replace V with prime. They're identical. I mean, they have got the same neighborhood. Okay, so I only need to check. Let's wipe out. I only need to check it for induced subgraphs that contain V and V prime. Okay, that contain V and V prime. But now, if this induced subgraph is not everything, so there's still something left here, then actually this graph is like this graph. I mean, let's maybe change color again to orange. This is this graph with V prime clones. Yeah. So I mean, if I have got a set, say A here, like the gray set was A, then G prime of A is actually G of A minus V prime plus V cloned. Yeah, plus V cloned. Okay, so if you just prove the statement by induction over the number of vertices, you have got from the induction that if you have got the orange graph and you clone the vertex, this graph is perfect. So the chi equals omega in this gray area just by induction. So the only thing that's left by induction, this is the trick we'll be using in all the proofs today, that you essentially need to prove only like this one for A equal V of G prime, that from the induction or from trivial arguments, this equality follows from everything except for the entire graph, and you want to prove for the entire graph. Yeah. So you have a graph, I mean, just to speak it in our terms, you have a graph, you clone the vertex, and you really want to check that after cloning this vertex, still chi equals omega for this graph, for the new graph, because for every induced subgraph, this is really either the induced subgraph of something that was already perfect, or this is a cloning in something smaller, and you can have like equality from the induction hypothesis. Okay, so the only task that's really to be done here is that, okay, I cloned V and I want to color the new graph with omega of G prime colors. Okay, so let's look at this omega of G prime. So let's look at this omega of G prime and how does omega of G prime relates to omega of G? Well, obviously it's not smaller because I mean this larger graph, we added some vertex, but we added just one vertex. Okay, we added just one vertex. So it's either equal or it's plus one. Yeah, so it's so omega of G prime is either equal or by that, cloning this vertex, you either increased omega by one or it stayed the same. And moreover, if you clone, and omega of G prime equals omega of G plus one, if and only if there exists a maximum clique K in G that contains V. Okay, so okay, you cloned the vertex and now V, you created a larger clique. That means that your original vertex needed to be in a maximum clique, a clique of size omega, and cloning this vertex made an extra vertex for this clique, so the clique enlarged. Okay, so here we've got this property that the clique size may grow by one, omega may grow by one by this operation, and this happens exactly when there was a maximum clique containing the vertex V. Okay, so we have got this property, and now the observation is that if if you have got that it grows by 1, this is what we said before, that if G pi is the maximum clique of G, then it grows by 1, okay, even only if it grows by 1. And then it's trivially to color G prime, because you have got one extra color. I mean, you grow the clique size, omega equal by 1, so you have got one extra color to color. So you can just color V with his own private color, like red, and just color the rest with the remaining omega colors, okay? So this is like trivial case. The difficult case is that, hey, that when omega didn't grow, you don't have an extra color. But if you don't have an extra color, you have got this assumption that V is not in any maximum clique of G. So for every maximum clique of G, V cannot be in a maximum clique of G. So we are cloning a vertex that's never in the maximum clique of your graph. And so how do we proceed? Okay, so, well, we know that G is perfect, so we can color it with omega colors. Yeah, so let's draw this graph here again. You have got this graph G. There's vertex V here that gets cloned to V prime. Okay, and let's color. And so we color these graphs, and maybe this will be colored red. This will be colored green. I mean, there's some violet area, blah, blah, blah. So we are coloring with the omega of G colors, and say V is red. Okay, good. Now the observation is that, hey, let's look at maximal cliques. So let's take black color, and how the maximal cliques look like. Well, maximal cliques of size omega need to have got one guy from each color. Okay, one guy from each color, just because, I mean, they need to be of size omega, and they cannot have two vertices from the same color. I mean, this is like the main fact we're using here, that independence and clique intersect in one vertex or are disjoint. Okay, so maximal cliques look like this, and they cannot contain V. So I really like maximal cliques look like this. Okay, the maximum cliques, the cliques of size omega look like this. Okay, so now the observation is that if I take the graph G and delete the color red, but not vertex V, so if I delete this area but keep the vertex V, then the omega drops by 1. Okay, if I delete this area, so I delete the entire red color, but vertex V, the omega drops by 1 because I intersected all maximum cliques. V was in no maximum clique, and so every other maximum clique needs to contain a red vertex, which is different than V. Okay, so this dropped by 1, so I could color it with less colors. What does it really mean? That means that I can recolor this guy. So this is what remains. Yeah, this is what remains. I can recolor it without using red. So I can recolor this. So I can recolor G minus red minus V with this number of colors, so like without using red. So I'm using the same colors as before, but I'm not using red. So in a sense, what it happens here, we are reshuffling this green, pink, and whatever colors are used here, so that V gets incorporated in this coloring without using the red color. Okay, but using red. So then we can use red for what was red and V prime. So we could use V prime as the new red vertex, and V gets swallowed into the rest. Okay, so let us repeat this proof. What happens here is that, hey, we are in this case when we cloned the vertex, but omega didn't grow. That means that this vertex wasn't in any maximum size clique of size omega. So we colored the graph and assumed that our color is red. And the crucial observation was that if we delete all vertices, all red vertices but V, already the clique size drops by 1 because there's no maximum clique including V, which means that you could recolor this red part of the graph so that V gets different color, so that V doesn't get red, it gets green, pink, or whatever. You can recolor this area here so that it uses only omega minus 1 colors, and then you can use the red color for what was red here and V prime instead of V. Okay, and because V prime has got the same neighborhood as V, it's still fine. There are no red to red edges in this coloring. Okay. Yeah, so this is the proof of this lemma. I think I finished here. Yeah, so this is like the punchline that was here on the picture before. I mean, you don't need to read it, and you don't need to read it. But yeah, so this is like what we get here. That perfect graphs are closed under taking clones. So you take a perfect graph, you clone one vertex, this is still perfect. Okay. So this is the lemma, and we're going to use now to prove the weak perfect graph theorem. So I said this is something called weak perfect graph theorem. Yeah, that perfect graphs are closed under taking complements. Okay. And so what do we really want to prove? Well, we have got perfect graph, and now we want to take its complement and prove that it's perfect. So what we really want to do, I mean, it's like, okay, again, we can take induction. So we can prove that more larger and larger. I mean, do induction over the number of vertices of the graph. So we prove that, okay, a single vertex graph, its complement, it's also a single vertex graph. It's trivially perfect. So actually, like, yeah. So what you do, you have got your graph, and you now want to say that the complement is perfect. So every induced subgraph of the complement has got chi equal omega. But for like the proper induced subgraphs, so like strictly smaller graphs, you get it from the induction hypothesis, yeah? Because an induced subgraph of the complement is a complement of your induced subgraph. So if you go to a smaller one, you know that the complement is perfect and all the inequalities are there. Yeah, so you really need to prove that omega of the complement equals chi of the complement. This is what we really want to prove here. And now the first observation is that omega of complement is alpha of g. Yeah, I mean, this is trivial, like maximum clique size of the complement is the maximum independent size of the original graph. But now let's interpret chi of g. This is just the chi of g complement is like covering the graph with cliques. Yeah, so color classes in the complement are independent sets. So there are cliques of the original graph. Okay. So what we really want to do here is that we want to prove, of course, there's equality in one direction, so we need to prove the inequality in the other direction. So we really want to prove that you can cover the vertices of the graph with alpha of g cliques. Okay? So this is like coloring of the complement is covering the graph with cliques, and now we need to use alpha of g, and we're strictly just to use alpha of g cliques, which is omega of g complement. Okay, so this is really what we need to do in this proof. So we need to do in the proof is, yeah. Okay, so we have a perfect graph, and we want to prove that its vertex set can be covered with alpha of g cliques. Okay, so let's do it naively, and this is like a good way of doing like coloring. So let's take a clique and color it red and proceed. Okay, so take some clique. So let's take our graph, take one clique, color it with one color, say red, and proceed. Okay. Okay, when we are happy, I mean, we have got induction, so and proceed means use the induction hypothesis. But when we are happy, well, if we color the clique and the alpha drops by 1, yeah, we used one color, so better alpha, which is actually lower bound on the number of colors we're going to use, better it drops down. Otherwise, we don't have any chance of using alpha colors to start from. Okay, because we just use one color and alpha stays the same. Okay, so if there is a clique that we can color so that the alpha drops by 1, so if there's a clique intersecting every maximum independent set, then we are done. Yeah, so if there exists a clique, okay, so for every max independent set, A intersection K is non-empty, then we are done. Yeah, if there's a clique that we can color and we intersect every maximum independent set, so with the independent sets drops by 1, then we are done. So let's look at the remaining case and let's try to reach contradiction there, because this is really what should happen. Yeah, I mean, there's a color class that drops alpha by 1, another color class drops the clique drops alpha by 1. So we really need to prove here that there is a clique that intersects every maximum size independent set. So let's assume the contrary. So the contrary says that for every clique, there is a maximum independent set that actually is disjoint with maximum size independent set that's actually disjoint with this clique. Yeah, so this is like this. Let's fix one such die. So let's define AK to be one fixed maximum independent. So for every clique, we fix one maximum independent set that is disjoint with this clique. Okay, and we're going to reach a contradiction with the fact that the graph is perfect. Okay, so we already departed. Let me observe here that we already departed from coloring really departed from coloring complement, we said that, hey, in the perfect graph, there must be a clique that enters every maximum independent set. So what we do it contrapositive, we say that, hey, for every clique, there's a disjoint maximum independent set, and we want to reach the contradiction of the assumption that the graph is perfect. Okay. So we want to use the previous lemma. And this is now the trick, the very nice trick of Lovaas, that actually, let's look at the weights of vertices. Okay, a weight of vertices is in how many independent sets it is. So we have got a family of, let's call it capital the calligraphic K to be the family of all cliques of the graph. I mean, you can think of all cliques or all maximal cliques. It actually doesn't matter, but let's look at all cliques of the graph. Okay, and every vertex counts in how many these like associated independent sets there are. Yeah, so we have got the family of cliques. To every clique, you associate this maximum independent set AK, and now every vertex counts in how many AKs it is. Okay, it counts in how many AKs it is, and this is the weight of the vertex. Okay, and now what we do, we take our graph, we take a vertex, look at its weight, say its weight is 3. That means that we make 2 clones of this vertex, so that actually this vertex becomes like 3 vertices. So we take every vertex and clone it sufficiently many times so that the number of copies is the original weight of the vertex. And if the weight was 0, we delete this vertex. Okay, we delete this vertex. Okay, so we make the G prime, but like now, if the original graph was just, I don't know, like looks like this was, then now, I mean, every graph, every vertex becomes like a cloud, actually a clique of vertices, like it becomes a cloud. This was weight 2, 3, this was weight 2, this was weight 4, this is weight 1. This is actually a cloud of vertices, and yeah. And become, I mean, this is G and this is G prime. So you're actually doing, and what we are doing here is that, okay, if there's vertex has got weight 0, you delete it. If vertex has got weight something, you make enough clones so that the number of copies of this vertex equals the original weight of the vertex. Okay. So what we obtained by this first, the main thing is that the previous lemma says that we get a perfect graph. Why? Because we started with a perfect graph, we deleted a few vertices, this is the perfect, like the guys of weight 0, and then we cloned some vertices to get appropriate weight, so like according to the weight. So this was just vertex addition that keeps graph perfect, and cloning that keeps the graph perfect. Okay, so we have got that our graph is perfect. Yeah, but what did we gain? In a sense, we can now project these AKs to disjoint independent sets. Yeah, what I want to say is that, hey, this AKs now a vertex was in weight. I mean, the weight of the vertex was the number of AKs it is in. Okay, and now it gets cloned into this number of copies, so you can assign a different copy to different AK. Okay, so now AKs you can project to disjoint independent sets that exactly cover the new graph. Okay, because like every vertex that gets cloned to exactly the number of copies into how many AKs it was in. Okay, so now these AK primes they exactly cover the new graph. So the number of vertices in the new graph is like, okay, each guy has got subset alpha, and the number of them is the number of cliques you take into account, like the size of the set capital K, the number of all cliques of this graph. Okay, the number of cliques. Yep. Okay, good. But what's the last question means, what's the clique size? What's the clique size of G prime? What's the clique size of G prime? Okay. Well, how does a clique forms in G prime? You need to take a clique. So you have got so remember there was a graph G, and you made it into like clouds in G prime. And now a clique here, I mean, if you look at a maximum clique, it takes everybody from one like cloning set, from like set of true trees. Yeah, I mean, there's no point in taking only a few of them. If they all fit, you can take all of them into your clique. So your clique here is really like a few set of this like true tree classes. Okay, and it projects back to a clique here. Okay, So a click here, K prime here, is actually a click here, and you blow up every vertex to a number of vertices. Yeah? So the size of K prime is actually sum over V in K, weight over V. So you take a click from G and just sum the weights of those vertices to get your click in your to get a click in G prime. Okay. So how big can the sum can be? How big this sum can be? And what I want to say here is the sum is smaller, strictly smaller than the number of clicks at the size of capital K, of calligraphic K. Okay, why? Because from every AK, you can have only one vertex. Okay, so now this is now the most important thing. I mean, I'm taking a click in G and summing the weights. Okay, now let's look at one AK. Let's look at one AK. Okay, at one set AK. Okay, it can contribute only one to the weight of the click. I mean, in this click. So let's take notation. So let's make face the gray area. Let's take click K and let's look at some other set, which is K hat. Okay, for some other K hat. Okay, it can intersect only in one vertex. Okay, so it contributes only one to the weight of one vertex unless it's disjoint. Okay, so we have got that this is actually smaller than the number of clicks, not larger than the number of clicks, because every AK can contribute only one to the weight of the one vertex of the click. Okay, but the AK is disjoint. Like for this particular click, there's one maximum independent set that's completely disjoint, because that was the definition of the AK. For this guy, there's this one, his guy, that's disjoint with him. So all of them contribute at most one, and this guy contributes 0. Okay, so it's actually strictly smaller. Yeah, it's strictly smaller because all the guys can contribute only one from this family of AKs, and one guy, this associated guy that was disjoint, is disjoint and he contributes 0. Okay, so what we have is that omega of G prime is strictly smaller than the number of clicks. Okay, it's strictly smaller than the number of clicks. Just because we looked at how these clicks are formed, they are from original gross and blown up, and the size of the blow up is the number of AKs intersecting the original click. Every guy intersects in one place, at most one place, except for this associated guy with this click that is disjoint. That makes a strict equality here. Okay, the last question is, what's alpha of G prime? Where you cannot, by deleting vertices, you cannot increase alpha, and by taking clones, you cannot increase alpha. Okay, and this is our contradiction. Yeah, we have got that the alpha is smaller than this, not larger. Omega is strictly smaller than this, but this number of vertices. So you have got no hopes of coloring with this number of colors, and each color of this size, of at most this size. Okay, because there are too many vertices here. Yeah, and this strict equality here now is the crucial part. Okay, the end of the proof. So what happens here, really? I mean, that's quite difficult. This is like a very tricky proof, in my opinion. So what happens here is that, hey, we're trying really to prove, by some easy reasonings and induction, we're really trying to prove that there's a click which intersects every maximum independent set. So we're assuming this is not the case for every click there's a disjoint independent set. And now what we're doing here is that, hey, we're doing some counting argument. Yeah, we are taking a graph where every vertex gets blown up to how many independent sets it is AK independent set was inside. And we're counting the vertices. The number of vertices is really like the number of clicks we took into account times the alpha. Okay. But the point is that the maximum click size, so the alpha in this process didn't increase, but the omega grew too little. The omega couldn't grow up to the number of clicks. It grows up to one less. And this is like the main reason why it happens is that, hey, a click in the blow up, every AK can contribute 1 to the blow up, except for this associated with this click. So there's one guy missing here. Okay, so this is a tricky proof. I don't have any better intuition to sell to you. I have got a second proof in the moment, which is like a linear algebra proof, which might be actually a bit more insightful for you here, but it depends on your taste. So let me take a sip of coffee and proceed. So what I want to do is that I want to present you a second proof now, which is I want to present you with the second proof, which I will prove something more. Sorry, I'll prove something a bit more. And namely, I will prove to you, oh, sorry, this is like the punchline here. I will prove to you more that, hey, the graph is perfect, even only for every induced subgraph, you have got the equality, the size of the subgraph is more than alpha times omega. Okay, so of course, I mean, there's one direction is triggering this proof. So let's look at this statement once again. I want to say that if a graph is perfect, then every induced subgraph you can color with omega colors, and every color class is at most alpha. So this equality is like trivial for perfect graphs, yeah, because I mean every induced subgraph you can color with omega colors. So there are omega colors, and each color class of size at most alpha. So this equality is like trivial after. So what I want to prove here is that this is like not only a necessary condition to be perfect, but also a sufficient one. So if in every induced subgraph you have got this equality, you know that you are perfect. Like the non-perfectness comes from the place when actually alpha times omega becomes too small compared to number of vertices. Okay, that this is like a different indicator of not being. This is like a really necessary and sufficient indicator of being perfect. Like there's no place when alpha times omega x doesn't match up to is smaller than the number of vertices of some induced subgraph. Okay, and maybe this angle will be a bit more intuitive for you. So let's try to do the other angle, and again the other angle is like okay, so what we do have that we now doing this direction. This direction means that we have got this equality, this inequality, and we want to prove that the graph is perfect. And we again can do induction over sum of vertices, which means that okay, for all smaller graphs this is true. But what do you have got? You have got the entire graph, and you know that for any set z inside, you have got this equality. Okay, which means that for any orange proper subset, any gray subset inside this orange subset has got this equality. So it means that by induction hypothesis, for any proper induced subgraph, you are perfect by induction hypothesis, because the assumption is satisfied for any induced subgraph of your graph. Okay, just trivially. So now you know that all your proper induced subgraphs are perfect and chi equals omega. Now you want to prove for the entire graph. Yeah, so you want to prove that for the entire graph chi equals omega. So what you really want to prove is you want to prove that you can color your graph with omega colors. Okay, so as in previous proof, we tried to cover the graph with alpha clicks. Now we are trying to color the graph with omega independent sets. Yeah, cover the graph with omega independent sets. So let's start as the previous one. Yeah, let's start with the previous one. I mean, take independent set, color it with red, and try to color rest. So what you really want to prove, this is like the same reasoning we had previously. You want to really prove in that if you have got, but now the assumption is this inequality. Now the assumption is this inequality that actually every independent set you want to really prove that there exists an independent set A, so that for each maximum click, K intersection A is non-empty. Yeah, you really want to prove that, hey, you can take a color that intersects every maximum click, so that once you delete this color, the maximum click size drops by 1, omega drops by 1. Okay, so this is like what you want to do. So like the bad case, which is like a symmetric bad case that previously, is that, hey, I want to prove that for every independent set, there is a clique Ka, which is disjoint with this there. So whatever independent set you choose, there's actually some clique here, that's maximum clique. So this clique of size omega, that's disjoint. So whatever you color red, there's still some omega clique left here, and omega didn't drop. Okay? And now we want to get into, so this is like statement sounds very symmetric and similar to what was before, but now our assumption is different. We're not assuming that the graph is perfect. We're looking at the complement, but we are having this assumption with these equalities, and now there are a few vertices in fact, and we're trying to get a contradiction here. That you, in a sense, the intuition is that you cannot get this property with only alpha times omega vertices. You need more vertices. Okay, but you cannot get, like, for every independent set at this joint maximum clique, you need more than alpha times omega vertices to have this one. So that's like what we want to prove here. Okay, good. So yeah, so let's delete the trivial parts and let's make space for that one. So we have got this assumption and we are trying to reach contradiction. So now what we want to do, now we are trying to make, intuition now is that we are trying to make a very complex structure of intersection structure. So the intuition from the linear algebra think that if there are a few vertices, you can't have a too complicated set family of like different strange intersections between them. We'll see that in a moment. Okay, let's do the following. Construction. So I take one independent set, maximum independent set. It has got vertices A1 up to A alpha. I'm using now the fact that I'm dropping alpha and omega are now for the entire graph G. Yeah, alpha is alpha of G, and omega is omega of G. Just not to put it of G everywhere. Okay, so I'm taking one independent set, and now I'm using induction hypothesis that if I drop one of these vertices here, I can color the graph with omega colors. Okay, so I'm just dropping one vertex and coloring the graph with omega colors. Okay, I'm dropping one vertex and dropping graph with omega colors, and this is like, so what I got here, I'm getting here really like omega independence. So I'm dropping this vertex, and there's like red color, there's an orange color, etc. Okay, and let these colors be A1 to A omega with superscript A. Okay, so what I produced really 1 plus omega times alpha independent sets. Okay, so there's independent sets I started from, and there's independent sets A1 1 up to A omega 1, A1 2 up to A omega 2, etc. Okay, I produced this number of independent sets. The key point that this is strictly more than the number of vertices of the graph. These are a lot of independent sets. Okay. And now what I want to do is that I want to produce cliques that intersect with them in a strange fashion. Okay. So the observation is as follows. Okay. Okay. So for any independent set, okay. So I have got these cliques, this independent set, and for every of this clique, I say this one, there's actually a K A omega 1. There's actually K A0. There's actually K A11. Okay, so there are these cliques, maximum cliques, that are disjoint with these independent sets. These are just independent sets, and I cannot use neither of them as like my first color of my coloring, of my optimum coloring. So there's always an independence and maximum clique disjoint with them, and just write them. Okay, so they're disjoint them. And let's see what are the intersection sizes between them. Okay, so these guys have got their empty intersections. On the diagonal, they're empty intersections. I'm just writing the intersection sizes between these sets. Okay. Okay, but what's the intersection of like K, I don't know, A I with a I prime J prime with a different guy, or A0? What's this intersection? Okay. So what we said, I mean, we are taking one from independent sets and the clique associated with a different one, and what's the intersection here? Well, the main observation is that so let's make the analysis here. Okay, so say say we have got a K which is a large clique. This is one of the K somethings. Okay. And say that it intersects A0 with an empty set. Yeah, so remember this picture, we had this A1 up to A omega, and now we deleted one of them and made the coloring up there. Okay, so what I want to say is that if there's a clique here, which is of size omega and is disjoint with this one, then hey, okay, if there's a clique, you deleted this guy and you made the coloring of the rest. So there's like red color, orange color, Okay, and you made an omega coloring. So maybe up there, you made an omega coloring, okay? And you made an omega coloring. So in the graph where this was still a maximum click, this was still a click of size omega, okay? So I want to say that this click needs to intersect every color class, okay? So what I want to say is that if this click is disjoint with A0, if the click is disjoint with A0, then whoever you deleted from here, this click needs to intersect every color class, okay? Because I mean, it's of click of size omega, which means that, okay, if the maximum click is disjoint with A0, it intersects all AIJs, okay? Just because it's a maximum click in this coloring. But also, for the same reason, if this click looks like this, so it gets here AI, then if you delete a different guy, if you delete, say, A omega, then again, this is a maximum click in what's you left, omega click in what's left. So you need to intersect every color class. That's written here, right? If you intersect in AI, then okay, for all the other guys, that's written here, for all the other guys, like if you delete a different guy, you're still intersecting every color class. And if you deleted this guy, then this becomes a click of size omega minus 1. So you're intersecting all but one color classes. So what we have proven here, is that there exists at most one A in the set A0 or AIJs, J such that K intersection A is empty. Yeah. What we have proven here, hey, if K intersects A0, doesn't intersect A0, intersects everybody else. If it intersects A0 is some vertex, it intersects everybody else for colorings with different deletion and misses one for the coloring with exactly like if you delete the intersection. Okay. So what we proved here is that I have got this sequence of like 1 plus omega times alpha independent sets. Okay. I have got this 1 plus omega times alpha independent sets here. And if I have got maximum click, I can be disjoint with only one of them. That's what we have proven. I cannot be disjoint with two of them. Yeah. That's what we did here by the case analysis. On the other hand, we had this, like, for every independent set, we have got this disjoint click. Okay. So now, if you now write this, all these guys, A0, A11, blah, 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 A1, A omega 1, blah, 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 up to A omega alpha. Okay. So if you draw these independent sets and you draw the clicks KA0, KA11, KA11, sorry, blah, 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 up to KA omega alpha, okay? And you make a matrix. What's the intersection size? So this is like, these numbers here are like how many guys are in the intersection. Then, well, by definition, on the diagonal, you have zeros, but you cannot have in any row, you cannot have more than 1 0. Yeah, that's what we have proven here. For any click, you can be disjoint with at most 1A. And of course, the intersection can be larger than 1 because the intersection of the independence and the click can be larger than 1. So you have got this matrix. Okay, you have got this matrix of these intersections. And the key point is that this matrix, this is 1 times omega times 1 plus, this is 1 plus alpha omega times 1 plus alpha omega matrix of full rank. Yeah, this is matrix of full rank. Okay, I mean, yeah, because it's like all this like linear independence rows. Okay, but now, so let's move it up and get some space. We have got this matrix. This was for A0, A11, blah, blah, blah. And this was like KA0, KA11, blah, blah, blah. And this is like the size of the intersection. Okay. But now I want to say, let's call this matrix M. Now I want to say that this one factorizes. Yeah. Because, hey, if you look at the, like, let's take the indication vector for k, I don't know, aij, let's take the indication of it. So 1 if there's a, so this is like 1 times n vector, which is like that's the indicator vector, which vertices are in this thing. Yeah, so let's call it 1 k ai1. Okay, and let's take a column being, I know, ai prime j prime being just again the indicator vector for this aij. And I want to say that the product, like the scalar product of this vector for k aij and 1 ai prime j prime, this is just the size of the intersection. Yeah, I mean, if you take this, the indicator vector scalar product, another indicator vector, I mean, everywhere where there's a vertex appearing in both sets, this ones will product will be multiplied by each other, and they will add 1 to the final scalar product. Okay. Yeah. So what I'm just going to say is that now, if you just make a matrix, okay, if you just now make a matrix that here, it's just make a matrix which are just indicator vectors of the case, and multiplied by the matrix, which is just indicator vectors of A's transposed, this will be in matrix M. Okay, you take the matrix, so you take the matrix with like rows being the indicator vectors of the case of the KAIs, and the other one, the columns are indicator vectors of the A's. Okay, and if you multiply these matrices, then in every cell you will have got the size of the intersection. Okay, so this matrix factorizes as this one's. Okay, but this is 1 times alpha omega times 1 plus alpha omega of full rank, and this is 1 plus alpha omega times the number of vertices, and this is number of vertices times 1 plus alpha omega. And this is a contradiction, yeah, because this is full rank, and we have got a factorization with like smaller rank, because if n is smaller than alpha times omega by this assumption. Okay, so you cannot, if you have a matrix, square matrix of full rank, you cannot factorize it as like product with like smaller dimension up there. I mean, this is basically linear algebra. Yeah, you cannot, I mean, this is like a linear transformation of the entire space, which is like bijective, so you cannot squeeze it into smaller dimension and then squeeze it back. Okay. So this is the final contradiction, and this is like the linear algebra way of saying you don't have space to fit all these guys there within alpha times omega vertices. You have got this object here that's like alpha omega plus 1 independent sets and alpha omega plus 1 cliques that intersect, like all of them intersect except for like every guy has got his own private guy which is disjoint with him, and apart from that everybody intersects in one vertex. And for that one, you need alpha omega plus 1 vertices just because of the rank reason. The end of that one. So this is the end of proof. I don't know if I don't know if you have got any questions here for that one or that one. This is the end of the proof. I wanted to say. I just wanted to say that I just Googled in the meantime the strong perfect graph theorem, because I felt a bit embarrassed. I forgot to check the exact set of authors there. So the strong perfect graph theorem was announced in 2002 by Trudnowski, Robertson, Seymour, and Thomas, and actually finally published in 2006. Yeah, this one that we discussed, that there are no odd cycles of like 5 or more, and not their complements. They're exactly the minimal vertex deletion minimal guys that are not perfect. Okay, so this is it. Are there any questions to the material before I stop the recording?